general, in X-ray, in X-ray astronomy, that's not what we've done, at least so far. If you have grating observations with, say, with Chandra or XMM, then you can do some of that. But mostly we're what optical astronomers would consider very low resolution in terms of, you know, when we're using CCDs like Chandra or XMM or, you know, or Swift or New Star or Nice or eRosita. So we're doing a somewhat different type of analysis, and as well as the lines, we cover a very wide bandpass. Typically, in any observation, we might be looking at 1.5 decades in energy. So it's like, sort of like going from the UV all the way to the infrared in the same go. And it's also true that the continuum shape often provides very important physical information. So we're generally looking globally at the properties of spectra. I know Richard Machotzi is giving the next talk, and he's going to make this point, I think, in even more detail because I originally stole it from him. So let's see. Now, here we are. Okay, so in general, we'll start with something like this, and this is just a random Chandra ACIS simulation I made. In all these plots that I show, and that they're made using XSpec, there's on the right-hand side, there's a list of XSpec commands that I use to make them. So I'm just doing this because you might find this helpful to. I'm afraid I didn't do it using PyXspec. I should probably do that as well. So anyway, we start with some observation like this, and if you've done any sort of X-ray spectroscopy, you sort of know this is roughly what things look like. And the model which went into this actually looked like that. So you see there's very many more lines than you could ever resolve with that ACIS spectrum. So the question is, what can we infer stuff like this from the the observation that we have here? So how do we go about doing that? And this is, I think, the only sort of little piece of mathematics I've got in this talk. So typically, we're observing some number d of counts in some channel from a source, and so the number of counts can sort of be described by this simple integral, where we've got a source flux. So you can consider that at the front of the telescope. There's some sort of energy-dependent effective area of the telescope system, and then the detector has some probability of putting an incoming photon of a given energy into a particular channel in the spectrometer. Again, T is the observation length. So if we sort of just turn this into a numerical problem, we're going to assume that the time, the factors about the instrument are all known, although I will return to that a bit at the end. So we're solving an integral equation for the flux. If we divide the energy range into m bins and turn this into a matrix equation, we get this rather simple matrix sum here. So we want to find the SJs. So if I carry on. If you've done any sort of matrix manipulation, then you've probably done first year as an undergraduate. You know that the way to solve a problem like this is to calculate the inverse of the matrix, pre-multiply by both sides and rearrange it. And in mathematics, that works fine. In astronomy, it doesn't work. What you find out is that the SJs you derive are very sensitive to slight changes in the data. you've basically got a great way of amplifying noise. Now, this is a very general problem. It's generally called the remote sensing problem. And it's not just in astronomy. You find this in geophysics. You find this in medical imaging. You do a CAT scan or something like that. The solar physicists have similar problems. And there are ways of stabilizing this sort of inversion. First developed in the 1960s by a Russian mathematician called Tikhonov. So if you're interested in about this, just Google Tikhonov regularization. And people over the years have tried various ways of doing this for X-ray spectra. But in general, I think it hasn't really taken off because we end up wanting to fit models which are parameterized in some way. So we might as well just build a system where we include all the things about the response when we build those models. So that's what we've done. And I have, this is my sort of standard plot about how most X-ray spectral analysis is done. And there's sort of a division between the scientist and the program. So what the scientist does is starts by defining a model. And then inside the program, you calculate the model, you multiply by this detector response, you compare to the data, and you sort of basically go around the loop. Have I finished? No. Okay, let's change the model parameters, recalculate the model, loop round again until I get to has the fit converged, and I have some criterion for that. I say yes. Okay, well, is it a good fit? And this is actually a really complicated question, which I'll come back to. If it is, yes, then I can carry on and do further analysis. If it isn't, then okay, I need to go back and refine what I think of as my model. So there are programs to do this. The one I've been involved with is XSpec. This is part of HereSoft, which is released by Goddard, and it's a general spectral fitting program. There's many models available. There's a Python version available as PyXspec. I think the other program that you're doing stuff with at this workshop is Sherpa. This is now available standalone. It was written as part of the CHOW, which is the Chandra Interactive Analysis System. It's a more general fitting program. It can fit images and other things as well. So, but one thing it does include is the XSpec model library. So there's a commonality between XSpec and Sherpa on that level, and Sherpa is a Python interface. There's a couple of other programs which you should probably know exist. There's a program called Specs, which comes out of Esron in the Netherlands. This is really it's a program which specializes in collisional plasmas and high-resolution spectroscopy. There are sort of more links built into it between the sort of atomic physics, and you can get certain types of information out easier than you can with XSpec and Sherpa. It's also a sort of independent set of models, although I think they are now working on being able to include the XSpec model library in that. But I think it is important that we have independent checks on some of the stuff we do, so that's good. There's another program called ISIS, which comes out of the MIT Chandra HETG group. That also can load in the XSpec model library. There are people who are enthusiastic about this. I think it has a less general use, and it has its own particular interface called slang, so it's not a Python-based thing. So the examples I'm going to all use are all drawn from XSpec because that's the thing I'm most familiar with, but you can generally do the same sorts of things with Sherpa and these other programs. Okay, so first I want to say something about the defining the model part of this. And the way I'm going to give this talk is I'm going to sort of go around all these little boxes. So my favorite statistical quote is from a statistician called George Box, which is, all models are wrong, but some are useful. So as astronomers and physicists, we're building models of the object we're looking at. We're using that to learn about things, but we always have to have in the back of our mind that probably the model is wrong at some level. But so we try and devise our models so that we're actually learning useful stuff. There is a tendency sometimes for people just to throw every single model they can think of at a spectrum, and I don't approve of that, and tend to, if I read papers where they've just done that, I take the paper less seriously. And in general, you can think of building up these models as out of components, which is sort of an emission component, so we call it additive, or something which modifies the spectrum, such as absorption. You call that multiplicative. So you can generally build up this model, which I gave a random example here, but you can make that as complicated as possible. So basic additive emission models, obviously, with things like black bodies, thermal brems, power laws, collisional plasmas, Gaussian Lorentzian lines. And the expect model library has been built up as ever more complicated models as people build up stuff, accretion disk, Comptonized plasmas, non-equilibrium plasmas, and so on. And then multiplicative is perhaps more simple, that you've just got things like photoelectric absorption due to our galaxy, ionized absorbers, high energy exponential roll-offs, cyclotron absorption lines, and so forth. There's another type of model which we call the convolution model, and that's just something where you take the current model as an input and you manipulate it in some way. And the obvious one is if you're doing some sort of smoothing with, say, Gaussian or Lorentzian functions. So if you're velocity broadening your spectrum, that's what you're doing there. And then Compton reflection again does that. And then there's some sort of instrumental type stuff like trying to model pileup on the CCDs. Okay, this was a table I made some time ago and is now out of date, but it was just an attempt to write down some of the physical processes and then the models in the expect model library which do this. And you can see there's a wide range of things. One of the problems, particularly, is if you're starting off in this field, is to know, well, what models should I be using? And generally, if you're a PhD student, then you depend on your advisor to point you in the right direction. In the expect manual, I do try and sort of include references for all the different models, so you can chase down the papers, things like that. Okay, and this is just a quick. If you've been trying out expect, and then you're just going to define a model, and then you're going to define some sets of parameters, and you can define sort of the ranges over which you're going to allow the parameters to vary, and so forth. And then that's just typically what you see. So just a general point about this expect model interface is it's fairly simple, and it enables people to write their own models and then fit them to their data. You can write so far in Fortran, C, C++, or Python. Although actually, if you write it in Python, you have to use PyExpect. I haven't yet sort of worked out how to hook Python stuff back into the non-Python program. Although I know it's possible in theory. So basically, all your model is doing is it takes in the energies in which to calculate the model and the current parameter values and writes back out the fluxes. And one of the challenges, particularly, I mean, people give me lots of models, but everyone uses their model on a specific type of data in a specific way. And then I often have to sort of tweak models to make sure that they'll work in cases where the original writer didn't think of. There's also a way of writing the standard format files, FITS files, which contain grids of model spectra. So you can make your own grids and then fit them without actually having to add a subroutine library. And I estimate about half the models in the XSpec model library are written by other people. So it's very much a collaborative effort. There's one other thing in XSpec, and I think Sherpa has something similar. There's an mdefine command which you can sort of define your own model as an arithmetic expression, which may include other XSpec models. This was just an example that I put together. If you wanted to make a model of a specific helium-like triplet emission line complex, where this is going back to the sort of the analysis of spectra as ratios between lines. You can look at the resonance forbidden and intercombination lines and the ratios from that. So this was just a way of defining a model which depends on those ratios. Okay. So going on to the next bit, the multiply by the detector response. So the way to think about this is at the top of the telescope, you've got some flux coming in, say between various energies. And then there are two operations that are being done. There's what we call the OFF, which is just the effective areas, and that's a vector. So that gives you photons per second coming into then sort of the detector part of the system. And we generally call that the RMF, and that's a matrix. And then that's going to give you your counts per second in the channel of the detector. So this is a typical OFF. Generally, any X-ray instrument sort of generally has a similar type of shape. The cutoff at low energies is usually because you've got some sort of filter in front, because you want to keep out, say, optical and infrared. And then there's a cutoff at the higher energies simply because the mirrors get less effective, because X-ray reflection has to happen at very shallow angles, and the higher the energy gets, the shallower the angles. So as you go to the high energy end of this, a smaller fraction of your mirror area can actually do the reflection. It's sort of, if you've got multiple shells, it's the innermost shells. And then there are usually features due to in this case, it's a CCD, so you've got silicon in the detector producing, and then features due to the mirror, which is iridium in this case. And then this is sort of an example of what the response looks like. This is for a 3 keV input X-ray. And this is the thing that actually sort of makes X-ray spectral analysis different and sometimes quite hard. You can see most of the time your detector tells you that, okay, it's a 3 keV X-ray, and there's some there's sort of roughly a Gaussian response with some width, but some of the X-ray, the detector basically loses part of the energy for a variety of different reasons. So you'll have an X-ray coming in at 3 keV, which is actually being registered at 1.4 keV or something like that. So in doing the modeling, you have to take that into account. And this can be quite important. For instance, if you have a source with a lot of absorption, so the lower energies are cut off, then practically, all the X-rays you actually are seeing at the lower energies are rarely X-rays which have higher energy, but the detector has lost part of their energy and so has registered them at lower energies. okay, this is just sort of in the, what are the analogs in UV optical. Generally, your response is very simple, and then you've just got a, the effect, the RF equivalent is sort of telescope reflectivities, detector efficiencies, filter transmissions, and so on. So usually you've just divided them out. But so can you ignore any of this response? And in very rare circumstances, the answer is yes. If you have a sort of standard CCD spectrum or whatever, you must use this RMF. With the Chandra HEGG spectra, you can just about get away with ignoring the response and just sort of basically fitting Gaussians. But you still need the RF section, obviously. With the XMM Newton, with the RGS, actually, if you try doing that, you get quite incorrect results, because you might think that the RGS is giving you a nice Gaussian shape, but in fact there are wide wings, so your line fluxes end up being wrong, and you overestimate continuum. So you have to be careful about things like that. Okay, comparing with the data. So we just need some sort of fit statistic where we're comparing the data and our model times response. And generally, you want to use a maximum likelihood estimator. So the easiest way of writing this is you're minimizing minus the log of the probability of seeing the data given the model times the response. And if you look in the XSpec manual in Appendix B, which is on the statistics, there's a discussion about what statistics to use and how they're derived and so on. So I recommend you look at that for general educational purposes. When Johannes talks about the whole Bayesian thing, of course, this probability of data given model times response is very important. So, okay, how's the fit converged? Well, usually you decide the fit is converged by it not finding a new better fit. But there is a problem with local minima. So this is a simple case where I've only got one parameter value, and I've got a statistic value on my y-axis. So if I'm approaching from the right-hand side of this plot, then I end up falling into this global minimum. But if I come from the left-hand side, then I fall into this other local minimum, and I don't ever get out to find the true best fit. So this is a problem which actually happens a lot. And the way that we're doing this, finding the new parameters, in the standard XSpec fit command, this is something called a Levenberg-Marquardt algorithm. Again, you can look that up. But you're using sort of local information. You take the current parameters and you calculate the derivative of the statistic with respect to the parameters, and then you move in. And the simplest case is just you move in the direction of the steepest downward gradient. It's actually a little more complicated than that. There are sort of multiple ways you can do this. The steepest descent, there's what's called quadratic, where you assume parameter space is quadratic, and then there's a combination, which in fact is what the Levenberg-Marquardt algorithm is. There are ways of sort of tweaking this. You can throw in a probability of actually increasing the statistic. So as a way of sort of jumping out of a local minimum. Also, I would note that there are some approximations that go in because you want to avoid numerical second derivatives, because that just blows up your noise. And then this is just showing XSpec running a fit. So you can see the parameter values changing, and then the first column labeled C statistic is the fit statistic, and you can see it runs until we're seeing no further change in that. The other two columns are tracking sort of other things about how well the fit's going. Okay, so I've just made this point that watch out for local minima. And my general rule on this, I think, is the more complicated your model and the more highly correlated the parameters, then the more likely that you're going to not find the absolute best fit. So one of the things I always encourage people is to actually think carefully about your model. If you've actually got parameters which are highly correlated, there may be a better way of writing your model because you're going to be hard to actually separate out information about those parameters independently. In the past, people have often sort of found the local minima just by running the expect error command or the step out commands, and accidentally finding a best fit. And you can sort of do that semi-automatically by actually telling expect if it finds a new minimum by doing using the error, then sort of do a restart. That often actually works reasonably well. So the obvious way around these sorts of local minima is to go to some sort of global method, of which a number have been tried over the years. There's things called simulated annealing genetic algorithms. In all cases, what you're doing is requiring a lot of function evaluation, so they're much slower, and you're still not guaranteed to find the true minimum. I would say probably a technique which is pretty much taken over astronomy is Markov chain Monte Carlo, which is a way of sampling parameter space. This is built into expect via the chain command, but you can also, if you're using PyExpect, you can also combine this with other types of MCMC code. There's also something called nested sampling, but this is what BXA does, so I'm going to leave that to Johannes. Okay, this was just a quick example of running an MCMC code in expect for a simple model where we're running through chain steps, and you can see the parameter measuring a photon index, and then you end up with this probability density plot. So you can sort of say the best fit is the peak of that plot, and then the width is telling you about how well you can determine that parameter. So then we get to the is this a good fit question, and I would say that okay, here's an example. So you do your fit, you end up with something like that, and my advice is always to look at plots. The human eye is very good at finding things. And of course, sometimes it's very good at finding things which are not there. But if you actually find something, it's a good way of then going and checking whether it's real. So what we've got here, the residuals, the data minus the model, and you can see sort of around 1 kV that there clearly seems to be some sort of systematic thing going on here. So this is probably not a good fit. Can I do better? Well, actually what I did, that particular model, I'd fix the abundance of the elements. So when I release that and let it go, and then and now if you look at the residuals, you can see it looks much better. So you can say, okay, that's obviously, I don't see anything obviously wrong here, but there's still the question is, okay, is this the best fit I can get? So I would say this, my experience is this is the most contentious issue in spectral fitting. everyone wants a nice simple test for whether they're using the correct model. Statisticians will actually tell you that if you have a statistic that you're using to find the best fit parameters, you shouldn't use that same statistic to do the test. And with chi-squared, that's actually all what we've done in astronomy for very many years. I'd say that the second most contentious issue then is comparing models. So the simplest case of that is what I've just done, where I had a model and now I've allowed one extra parameter in there. So is that statistically significant? Am I justified in doing that? Well, there are standard tests for that, like the F test, which is a variety of the likelihood ratio test. But there are subtleties in using these. And generally, I recommend you always test stuff with simulations. And then I mean, that's the simple case, but then the more complicated case is, I have, what happens if I have two totally different models? I don't know whether my source is a thermal or non-thermal, Do I compare a thermal Bremsstrahlung with a power law? If I get different best fit parameters, can I tell that whether which one's better? Is one of them statistically better? So this is generally called the model selection problem, and it's actually, I think that is something that the Bayesian methods are particularly good at. So again, I'm passing all the interesting questions off onto Johannes. I would say on the question about is it a best fit or is it a good fit, just as a sort of yes or no hypothesis test question, that even seems to be quite controversial among statisticians, that there is arguments about whether it even makes sense to ask that question. Of course, that's no help if you're writing a paper and the referee comes back and says, is your model, you've fitted this model, is it actually a good fit? Then you're not going to get the paper published by telling them that statisticians disagree on whether that's a meaningful question. Okay, and then there's the calculate confidence regions. So how we've done what is called a point estimate, which is basically we've got the best fit has these particular parameter values, but what's the range over which they're reasonable. So if you do an expect fit, then at the end of the fit, you see it'll give parameter value plus or minus, and those are actually 1 sigma error estimates based from the second derivatives of the fit statistic. So they should just be thought of as estimates. The error command itself tries different values of the parameter while minimizing the statistic over all the other parameters until it finds a required increase in statistic value from the minimum. That's a better estimate of the error than the simple plus or minus. It's not ideal either because you're not really taking into account correlations between parameters. Generally, you're not just interested in one parameter, you're interested in the whole set of them. And again, this is where things like the MCMC, I think, really win out. And again, you want to produce in a Bayesian sense, you want to produce a complete probability distribution of the parameters. Okay, just something about background. If you're looking at a bright point source with Chandra, and it's near the center of the field of view, so the resolution is really good, you may be able to get away with not worrying about the background, but generally there's some background component to the spectrum in addition to the source model. So traditionally, the way this has been handled in X-ray spectroscopy is you extract a spectrum from another part of the image, or if you're really unlucky, another observation, and then you include this in when you're doing the fitting. If you're in a Gaussian case, then everyone knows how to do this. You can just subtract one from the other and sum the errors in quadrature. Unfortunately, that's generally not the case in X-ray astronomy when we're generally in the Poisson regime, and you can't actually just subtract two Poisson variables and get a nice simple solution to this. I would say that the correct way of dealing with all this is to actually have a model both for your source and for the background, fit them simultaneously, and fit your two sets of data simultaneously. So basically you have a model for the background which is being fit to both the source spectrum and the background spectrum, and its parameters are held to be the same. And then you've got a model of the source which is being fit to the source spectrum. So you simultaneously solve for the model of the background and the model of the source. I've just included here a couple of references for papers which did that. The problem, of course, is actually having a good model for the background. And one of the things we talk about is sort of building up a collection of good background models for all the different detectors. And that's sort of on its way, but we haven't really done it properly yet. And this was just a summary of how you do that simultaneous fitting of the source and the background. So with your source model, both the source and background models, you're multiplying by the instrument response. If you have different size source and background regions, and you assume the background is sort of more or less uniform, then you obviously scale by the areas, and you then calculate your fit statistics for the source and the background spectrum, and you sum them up, and you minimize that. So that's fine. Another thing to watch out for, in the past, people have sort of routinely used chi-squared as a statistic. This goes wrong if you don't have that many counts. If you end up having if you see some fit which looks like this, where you basically got all the data points appear to be above the line, but it claims that it's reached the best fit, that's a good indicator of this problem. In fact, what's happened in this case is that I've actually binned up the data in the plot. So if I'd unbid it, what you will see there'll be lots of points in here with basically zero counts in them, and or very few counts, and those fluctuations actually is the positive fluctuations give more weight than the negative ones. So it actually biases the model. So anyway, generally you shouldn't be using chi-squared, but people do, so watch out for that. The way you can actually bin up your spectrum. I'm always a little suspicious about this because you're binning up something based on the spectrum itself, so it's a little difficult to quantify what the bias is. There's an optimal scheme worked out by Castro and Bleeker based on the resolution of the detector and the number of counts, and you can use that, for instance, in the tool FT Group PHA. You can actually use this even if you're using the correct C statistic for Poisson data. In fact, people have told me that actually this works quite well. It actually helps doing the fitting a lot. So as I say, you should use this C statistic, which is named after Cash. There's a you can go back and look at the paper by Webster Cash on where he devised this from the maximum likelihood statistic for the Poisson. There are some tricks. If you really must use chi-squared, there are some tricks where you can actually change the weighting. There's a weight Churyshov option in expect, which is the one that I prefer to go with. Anyway, I've given you another link to something here, and also look again in the statistics appendix in the expect manual. Okay, I'm going to finish up by just talking what sort of challenges are coming along. We've got new types of data. There's spectropolarimetry. There is the satellite IXPE, which is now taking data. This is totally fake data, so it won't actually look like this. But when you're doing spectropolarimetry, you'll have 3 spectra at a time for the 3 Stokes parameters. I've shown the I, U, and Q. So we have to build models which are predicting the different things based on which Stokes parameter is. So this is all going to be in the next release of expect. So that's something I've been working on recently in collaboration with parts of the IXPE team. So other challenges which are going on. We've got the microcalorimeter data. So CRISM, which will be launching shortly. We had a very brief taste of this with Hitomi, with the observations of the Perseus cluster. And one of the things that we realized from that, the problem with calorimeters is you get very good resolution, but similar to CCDs, there are still these detector effects which cause you to have the response going down to low energies. So you might have a 16,000 by 16,000 matrix, which is basically a triangular matrix. So you've got 16,000 squared divided by 2 elements, and that gets quite large. And because the speed of the fitting goes as the number of non-zero elements in the response, it can be quite slow. So we've been devising techniques for getting around that. We have something which seems to be working reasonably well. Basically, in sort of dividing the response up into high resolution and low resolution parts, and the low resolution part doesn't have to have as many bins in it. So yeah, we've got sort of 2 order of magnitude speed ups in our fitting so far. So that's good. Looking a bit further ahead with missions like Athena, which is the European flagship mission coming up next decade, which again, there'll be calorimeters, but there'll be many more individual measurements. So you'll be looking at extended source, and you're going to have to be dealing more with data cubes and individual spectra. I mean, that's started a little with Chandra on XMM, but it's going to be a much bigger issue. So there's probably going to be people are going to have to think of some entirely new ways of doing the analysis. Two other challenges at the moment, which we're thinking about, is how to deal with uncertainty in models. So I've been talking about the uncertainty we have on the data, and I've been assuming that the models are correct. However, we depend on atomic physics measurements. There are uncertainties in those. So there are uncertainties in line strengths. There are uncertainties in line energies. As we go to high resolution data, that starts to matter. So we're at the moment we're sort of experimenting with this, but we haven't got a complete solution yet. And then there's also uncertainties in calibration. The obvious one in that is that absolute effective areas are very hard to determine. So if you have observations with multiple from multiple telescopes, your normalization or your total flux measured might differ by 10%. And for some things that you're not really that worried about what the total normalization, but there are science cases where this really matters a lot, particularly using things like clusters of galaxies for cosmology. So we're working on firstly actually just being able to know what those numbers are, what the uncertainties are. There's an organization called IACHEC where we get together with people from all the different missions and try and compare notes. But then in general, we want ways of including this in the fitting. So we'll be determining stuff about our instrument at the same time as determining stuff about our source. So again, this is sort of something that we're working on. Just wanted to note a couple of things about these sort of random bits and pieces I've got at the end. So the standard expect interface is written in TCL and it's difficult. So we put together a Python interface. It's basically running the standard expect underneath. You can get some of the internal expect data out, so you can use it in other Python packages. For instance, you can do plotting using matplotlib. So this is just the link to the Python version, and then this might be helpful for people, but I put together on GitHub that there's some Jupyter notebooks showing different types of analysis using PyExpect. In particular, how to sort of do some of the plotting. One other thing, I wrote a, that's telling me my time is up. I wrote a library and Python package which reads, manipulates all the file types used by expect, called here SP. So that's something you can build on if you're doing other things. And then there are a set of tools built on top of that. I'd mentioned the FT group PHA one earlier. And this is just links to everything. So I'm including this in. I assume that you've already been given all the expect and Sherpa stuff anyhow. But this will be in the presentation. And then my final one is I have to mention this, that I and some colleagues put together a book a few years ago, Handbook of X-ray Astronomy. It's relatively short, but it's sort of designed for people who are just getting into the field, and we tried to give some of the background. So if your library doesn't have this, then suggest they get a copy. I should say I don't make any money out of this. Deliberately arranged it so that I don't get the royalties. So that's
okay, thank you very much.
Yeah, so great.
Okay, so questions.
I see some stuff in chat.
Yeah, on the chat. If there is no question from the audience first.
Yeah.
Okay, so think about it and we can go to chat.
Yeah. You want to read the questions or shall I just read them?
You can choose your favorite questions first.
Well, I see Martin Topinka has been very very good here and asked a bunch of questions, so thank you. So he says C-stats means the Poisson distribution of the counts and therefore not the standard maximum likelihood formula to minimize. Or does it mean something? No. So the statistic is the maximum likelihood formula for when you have a Poisson distribution of counts. Again, I'm going to refer people to the statistics appendix in the expect manual, where I actually give the formulas and everything. Okay, please, what is your non-Bayesian cookbook to compare two models? Sounds like not just compared reduced chi-squared, especially in the case of non-nested models. Yeah, this is really tough. I mean, there are ways you can sort of do simulations saying if I I'm not sure I can give an easy answer to this. I mean, I think the frequencies answer to this is probably that you can't do that. I mean, you can do tricks. Well, actually, no, even that doesn't work.
Thank you. Actually, the reason why I ask is because like most of the papers, they compare models and they say the best one is the one with the lowest reduced chi-square, and that's the end of the story. And I understood that it's probably like sometimes comparing apples and oranges, that you had the best reduced within the set of the models, but if you compare two different families, it's getting to be tricky.
Yeah, that's right. I mean, you can obviously say that this is the one which gave the best fit statistic, but the question is it enough of a better fit statistic than you can rule out the other one? I mean, I generally fall back in these things is to saying, you know, it's a scientific judgment what model you're trying to fit. So, you know, and you may hopefully that there's other information that you have that will be telling you that I should be choosing this particular model rather than this other model. But, as I say, I sort of fall back on. I mean, the whole, yeah, just look at stuff about model selection. You know, there are good Bayesian approaches to this, and I'm less convinced that there are good frequentist approaches. Let's see, one more question. One more guess that binning at any coarser bins than what is the instrument binning leads to loss of information. Yes. Yeah, that's true. One of the issues actually here is that the people who build the instruments have a tendency to put in very many more bins than their resolution is actually for. I mean, you know, and they like to give you all of that. So, in fact, there are cases where you bin stuff up and you're not losing any information whatsoever. If you're doing that before you look at the data, that's fine. You know, if I'm and I did this, I seem to remember on the Suzaku mission, we worked out a sort of standard way of binning, which should operate on, which you should use for all data, simply because that when they set up the instrument, they had far too many channels for the resolution. So we had then a standard set of binning, and you did that, everything ran much faster, you weren't losing any information. The thing that worries me is if you look at if you decide you're binning after looking at the data, you might be losing information about absorption features. So you do have to be a bit careful about that. The Castor and Bleecker thing is actually based on information theory. They went back to Shannon, the Shannon criterion, and actually derived what the information is in there based on the resolution and the number of counts. So yeah, check out that paper. And as I say, some people who've done quite a lot of analysis of different sources, whom I respect for this, have actually used the Castor and Bleecker thing and say it really does help quite a lot. It speeds things up. It seems to make stuff a bit more stable. But again, they're still using the C statistic. They're not binning it up in order to do chi-squared, which I really do not approve of.
Thank you very much indeed.
Sure. Any other questions?
Yeah, thank you. We have a question or comment here from Gabriela.
Hello, Keith. I just want to add something to that. I'm actually about to publish a paper where I look all the absorption features in a sample for like 22 sources. And what I did, I tried to, before I looked at the data, I looked at different type of binning. I did the standard binning, and then I included the Castor-Bleecker binning. And I found that it was incredible. I mean, the information that you can get out with that binning is incredible. I mean, it's much better than the other standard binning. So I'm actually going to write something that where I compare different binning, and I can actually say that, you know, especially if the absorption features are not that strong, but you get, I mean, I actually really compare, and it really helps a lot, which is a new thing. So I believe that from now on, we need to use the Castor-Bleecker binning. It's the only way. It's the only way forward, really.
Great. That's very good to hear. Thank you. I'll look forward to seeing that paper.
Okay, one more question or comment supporting or.
Thank you. Hi, I have a question about spectropolarimetry. I wanted to ask if the background for the Stokes parameter is handled the same way of the background of energy spectra in XSpec.
I think the answer to that is yes. However, I don't think this is something that we've thought about that much yet, because you're going to be looking at very bright sources. Because the polarimetry signal is small, and it's going to be bright sources for long observations. So my suspicion is that the background won't be that important. The real thing is actually going to be understanding systematic errors. But I should say I'm not part of the XP team. I've just been working with them on this. So I think they're still in the stage, they're basically making their first science observation of Cas A at the moment. So they're still in the stage of actually sort of trying to get things going and understand things. So I've got what I guess we could think of as the initial stuff in XSpec, but I'm fairly sure that there's going to be changes as they understand their system better.
Okay, thanks.
Sure.
Any more questions? Comments? Maybe I would like to ask about binning. When you mentioned CRISM,
right?
You mentioned that there will be different energy ranges with different binnings, maybe for the speeding up the fitting process. It will be defined based on the decision of the astrophysicist and decision of what you are fitting. So depending on the model, whether you expect more lines in some region or other, or would it be like standard tool like for future fitting, so that there will be recommended binning, like let's say at higher energies, maybe where you don't expect many lines, so you don't need such a high spectral resolution. How did you test it actually?
No, that's actually not what I'm talking about. We may, I mean, we may end up doing some sort of binning like that. I mean, because obviously there are parts of the spectrum where you're not expecting to see any lines, so it might make sense to bin up there. But no, this is actually something we're trying to do where you're not binning the data up in any way whatsoever.
Mm-hmm.
But what you're doing is actually changing the way you handle the response, because the response can be thought of as having sort of high resolution components and low resolution components. So the idea is to split it into two responses. So what you do is you calculate your model at the high resolution. You multiply that model by the response, which is which has all the high resolution parts, and that's going to consist of a fairly sparse matrix. It's mostly going to be zeros, so that will be relatively quick. Do that, and then what you do is you actually then bin up your model and multiply that by this lower resolution response, which has fewer energy bins, bigger energy bins in it, because that's a response which is just slowly changing with energy. And then what you do, and those two of them will give you your model, predicted model spectra, and then you add them back together again, and then you compare that with the data. So we haven't binned the data up in any way.
Okay.
So, but it gives us an order of magnitude or two speed up in actually that step of multiplying the model by the response. So, and we've done a bunch of tests on this, and it seems to work pretty well.
Okay, I see. Thanks.
Sure.
Yes. Yeah, there is Thank Liu raising hand.
Hello. Hello, thank you for the talk. I want to ask a question about background modeling. It is often the case that we have a faint source with low signal-to ratio, but since we can extract background from a larger region, the background spectrum would have a much better signal-to ratio. And the background spectrum is often complex, has some complex features like many emission lines. And the model is, of course, complex. So when we fit the source and background simultaneously, with such a complex model of the background, actually the statistics would be completely dominated by the background. We cannot really extract any information from the source then. Therefore, in practice, generally, I would always fit the background first and then freeze all the parameters, leaving only the normalization, and then fit the source and background simultaneously. But I have always been a little worried about doing this. So I want to ask your opinion about it. Do you think it is correct, or do you have any better suggestions? Thanks.
Yeah, I mean, that's certainly a better thing to do than the just taking data, subtracting data from subtracting the background from the source. So you've done the next step along, and yeah, I agree with your point about the difficulties with complex background models. So I think what you're doing is, I mean, it's not totally wrong. It's a reasonable approach to take. I mean, ideally you would like to be including sort of some uncertainty in that background model in what you do. In practice, it might not matter. If you've got enough data, then that background model is very well determined. So it's not going to make a big difference. But I would definitely try and get some idea about how whether that's actually a significant factor. I mean, in a sense, again, I'm going to go, if I go Bayesian here, I mean, you can, it's probably possible to build up a system so that you're using the sort of posterior probabilities on all the parameters in the background, and combining that with the uncertainties that you're getting from the source. But yeah, again, I mean, I agree. This is a fairly difficult problem to actually do correctly, and you're certainly doing what I think is a reasonable approximation way of doing it. So sorry, I can't give a really precise answer to that. But I agree. I mean, you're good to be worrying about things like that.
Thanks.
Thank you. Any more questions? Yeah, on Slack, yeah.
So Johannes was asking if you could expand on how you would set up simulations to decide whether a delta C stat is significant.
Okay. So this is the problem about if you're adding a component or so on. Yeah. I'm just trying to think of whether I've got a good example somewhere. I might go in. Check whether I put something. No, I'm trying to find whether I have a good web page or something where I actually go through all that, because I mean, it's basically that what you're going to do is you're always asking the question, is the set of simulations, I make a set of simulations of something, and then is the data that I see, can it reasonably be said to be drawn from that set of simulations? So it's a matter of sort of comparing sets of simulations with and without the extra component, and comparing that to the data. But somewhere I have a nice sort of flowchart type thing of that, which I was trying to find but can't immediately off the top of my head. It's actually probably in that X-ray astronomy handbook book.
Okay, great. Thank you.
Sure.
Yeah, any more questions? Well, if not, then thanks a lot, Keith, for a very nice lecture.
Well, you're welcome, and good luck with everyone's work at the workshop.
Thank you very much.
I will look forward to actually listening to some of the other talks.